Hi, this is Kevin Ega, bringing you Calculus 3, Math 250. Welcome back to Lecture 5. Before I begin, I wanted to mention at the beginning of the semester, I mentioned that there was a recommended book. This was not a required textbook, but many students have found this helpful. I don't know how many of you have gotten it already, how many of you maybe it's still back at Pepperdine and you don't have access to it now. That's okay. I think whenever you get around to reading it, that would be. Um, I think some people have found it useful to get a different perspective. This takes sort of the opposite perspective that the textbook does, and many people like that. So um, if you're just kind of looking for a different way of somebody explaining it, you might enjoy that. Um, if you don't have that, you might look around for it in your local library or local bookstore, or buy it online. All right, so let's um, let's talk a little bit about where we've been. So one thing that we talked about a bunch in the past couple of lectures are these ideas. So we want to know if a vector field is conservative. Okay, F is conservative. That's this line right here. F is conservative. And there's uh, I'm going to call the x component P and the y component Q. This is in 2 dimensions. Okay, and of course, a similar diagram could be written for 3 dimensions. Okay. It's equivalent to these line integrals being independent of path. Integral p dx plus q dy, also known as integral of f dot dr. Okay, that's independent of path. It just depends on the endpoints, and that's equivalent to, in turn, these line integrals being 0 when they're closed loops. Okay, so for closed loops, we get this being 0. All of these 3 we proved are equivalent. And we know if f is conservative, then q sub x is equal to p sub y. Okay, the Clairaut kind of result. So one thing that we have left open is whether or not this implies the other thing. So let's say q sub x equals p sub y. Does that mean that these other things are true? And well, one thing that's going to be helpful to address that question is Green's theorem. So remember last time I introduced this theorem here. You have a region D. We're going to take the boundary of D counterclockwise, and the line integral of p dx plus q dy is equal to the double integral over the region D of partial derivative of q with respect to x minus partial derivative of p with respect to y dA. Of course, the relevance here is this looks a lot like Clairaut's result. Clairaut's condition here is qx equals py, and if qx is equal to py here, then that should be 0. So let's take a look. Okay, this condition here, okay, integral of p dx plus q dy, that's what we have on this side here. And here's the point. It sounds like this is a really useless kind of condition to have to test whether a vector field is conservative. I mean, let's put it this way. Let's say somebody handed you a vector field, give you a p and give you a q. Clairaut's result, that's easy to use. You just see if they're equal. Q sub x, see if it's equal to p sub y. This one seems really hard to verify. I mean, you could verify it for any curve, but you have to check it for every curve. That's a lot of curves, right? So that doesn't seem like it's really promising until you meet Green's theorem. So in Green's theorem, here's what you're going to do. Let's say q sub x is equal to p sub y. Okay, let's say this is true. We want to know if this is true. If so, then this would imply this, and then this would imply this would imply this, and then all of these things would be equivalent. So if I can prove that q sub x equals p sub y implies this top result, then I'd be done. Okay, and so what I need to do is I want to say, let's C be any closed loop. I don't want to compute what this is. So let C be any loop in the plane. We want to show that this integral is equal to 0. So this loop is going to enclose some region, call that D. Then by Green's theorem, this is equal to this. Okay, and if q sub x equals p sub y, then this is 0. So we're integrating 0, And when I integrate 0, I get 0. And there we go. The integral of p dx plus q dy is equal to 0. So if q sub x equals p sub y, then this integral is 0. And it looks like this implies that. There's only one problem with this. It's wrong. Or at least it's a little naive. There's a wrinkle in this argument that I need to address. And that is, I actually have a counterexample. Okay? Take a look at this. Look at this vector field. Okay, maybe a little complicated looking. Don't worry. This is p. This is q. Take the partial derivative of p with respect to y. You can use the quotient rule here. This gets squared, and then this times the derivative of this with respect to y, which is this times -1, minus negative y times the derivative of this, which is 2y. Okay, expand this out, and the minus y squared and the 2y squared combine to make a plus y squared, so you get minus x squared plus y squared over x squared plus y squared squared. And look at this one, q is equal to this. Take the partial derivative of this with respect to x. And again, you're going to use the quotient rule, okay? And we have x squared and minus 2x squared. They combine to make negative x squared here plus y squared. And there you go. This and this match exactly. So q sub x equals p sub y, right? According to this, that's Clairaut's result. That should imply all of these things. In particular, what we should any closed loop will have this integral being 0. Okay. Let's try this one, the unit circle. Okay, this is the same vector field. I'm going to use the unit circle. X equals cosine t, y equals sine t. T goes from 0 to 2 pi. And now the integral of f dr is going to be the integral from 0 to 2 pi of this times dx dt plus this times dy dt on dt. Okay, that's how we do these line integrals. You just plug these in, sine t here, cosine t for x. Dx dt is going to be negative sine t. Dy dt is going to be cosine t. And we get this. Okay. Cosine squared t plus sine squared t, this bottom part is going to be 1. And then we're going to get sine squared t, we're going to get cosine squared t, we can add this up. This is going to be 1 here, the integral from 0 to 2 pi dt, that's just 2 pi. Hold on here, that's the integral of f dot dr. This is the integral of p dx plus q dy. That's not 0, it's 2 pi. So this is true, qx equals py, and this is false. This integral of p dx plus q dy is 2 pi, not 0. So this is true, this is false. So it's not possible that this implies this. Uh-oh. What just happened? Did we find a flaw in the logical structure of mathematics? No, actually, we just weren't careful enough. We just weren't careful enough. Well, let's verify a couple of things first. You can actually see this just in pictures, just in case you were worried about the computation. Here's the actual vector field here. Okay, and as you traverse this unit circle counterclockwise, you will see that this is always going along the vector field. So remember, this is tangent vector field t, and sorry, tangent field t, and this is the vector field. It's pointing in the same direction. F dot dr is going to be positive at every point. When you're integrating something that's positive, it's going to be positive. Okay? You're going along this loop here, and always going with the arrows. So this integral is always positive. As we saw earlier, it was 2 pi. But the important thing is it's not 0. Okay. So in particular, it's not conservative. Another way of viewing this is if it were conservative, I start here and I go up here, I'm going in the direction of what is purportedly the gradient of a function, right? If this is conservative, then it's the gradient of the function. And then so the values are increasing, because I'm just going along the gradient, right? And I come back to where I started. And somehow, all that time, I should have been increasing in the value of the function, or whatever function that was. But how is it possible that I get the same value as when I started? That doesn't make sense. So yeah, f is definitely not conservative. By the way, in case you think this picture looks a little familiar, we didn't see it before, but we saw something kind of similar. Um, Remember this one? This was an example that I brought up a couple times before. Negative y comma x, and again, the arrows are going around in a circle like this. Okay. This one, by the way, is not a contradiction. Does not give a contradiction to the argument that we have. It is also true that the integral is positive, but um, q sub x and p sub y are different. Right? Q sub x, that's the derivative of this with respect to x, is 1. Partial derivative of this with respect to y is negative 1. This does not purport to satisfy Clairaut's condition for being a gradient of anything. So this is not even trying to be the gradient of something, and indeed it fails. This one, you'll notice it's a lot like this, except that you've got this extra denominator here of x squared plus y squared. Other than that, it's exactly the same thing. That's why it looks like this. The arrow's pointing the same direction, it's just rescaled. It's rescaled. Over here, in this one, the vectors were close to 0 around the origin, and they get larger and larger as you go further and further out. Here, it's the other way around. Because it's divided by x squared plus y squared, okay, out here, they're very small, and as they get closer and closer in, they get larger and larger. And you notice that at this point, it becomes sort of almost unreadable exactly what's happening here. And at the origin, this thing goes to infinity here. Okay. This is actually, that observation is actually at the heart of what's maybe going on here. Okay, let's actually try to do the Green's theorem thing. We have this loop here. It encloses a region D. And the idea is Green's theorem should say this is equal to this, but somehow that failed, right? This one here was 2 pi, and this one here was 0. In this region, we're integrating 0. Now, here's the thing. At the origin, we had infinity. Now, it's 0 everywhere here, except that in the origin, you'd think the integral would still be 0. And it would be, I guess. It's a little hard to be sure because it's not clear how you define things when there's a point where things go to infinity. But it seems like you're going to cover almost all of D with you know, rectangles, and over each rectangle, I mean, unless you choose the origin, you're going to get 0. So what's the deal here? Well, let's look at Green's theorem. I've been focusing on this equation here and this picture here, but I didn't tell you about this bit here. Okay, if you look in the textbook brings up a whole bunch of conditions here, most of which define what is D, what is boundary of D, and things like this. But also, Q sub x and P sub y have to be continuous. In particular, they have to exist. And if there's any point in here where they don't exist, then Green's theorem doesn't apply. In a way, this is kind of shocking. I mean, look, I mean, it mostly works. It's just missing a point, right? What's one point among all these other points, right? But we have to then realize that actually Green's theorem actually does not work when you're just missing a single point. Actually, this comes down to the same effect with the fundamental theorem of calculus. In fact, in the proof of Green's theorem, I was depending on the fundamental theorem of calculus in precisely this way. Okay. And so what do we have here? We have this region here, except that we can't apply Green's theorem because it's not continuous. These Q sub x and P sub y are not continuous at the origin. And in particular, it's not continuous everywhere in the region D. So Green's theorem does not work. Okay, so we talked about integrals on a curve called like C1. That was 2 pi. Integrals on, let's say do an integral on C2. Now in C2, that is around, that encloses a disk-shaped region. And this one, in this region, everything's fine. Partial derivative this with respect to y, partial derivative of this one with respect to x, those are both continuous here. The only problem is when this bottom is 0, and that's x squared plus y squared equals 0 is this the origin. As long as I don't include the origin, Green's theorem would work. And in fact, if I take the integral around any such loop here, I'm going to get 0. So the integral on C1 is 2 pi. The integral on C2 is 0. What about integrals on C3? Here I've drawn another shape here. It's an ellipse, okay, around the origin. Again, I cannot say that it's 0 because it's including the origin. Just like C1, I can't say that it's 0. All right, to understand what's going on here, I want you to recall these weird regions, this annulus, for example, from the other day. So, remember I said the Green's theorem looks like this. If I want to take the double integral on this annulus of q sub x minus p sub y, then really I've got two pieces. I've got this piece of the boundary, okay, and I've got this piece of the boundary, and they go in opposite directions. This is going counterclockwise, this one's going clockwise. And if I add these integrals, then I'm going to get this double integral. All right. So in this case here, okay, let's say we have C1 goes this way, C3 goes this way. They're both going counterclockwise. Negative C3 will go this other way. Okay, that's what we want to look at. So we've got C1 going this way, negative C3 going that way, and then the integral of C1 plus the integral of negative C3 is going to be 0. It's going to be this double integral of qx minus py. This is going to be 0, and there's no problem here because where it went to infinity is not in the region D. It's out here. It's kind of weird to talk about this as being outside, but there you go. It's not in the shaded region. Okay. And so integrating 0, that will give you 0. And so this integral of C1 plus integral of this minus C3 is 0. Of course, if I switch the order of C3 back, then the sign changes to a minus. So this integral of C1 minus integral of C3, which go the same way, is equal to 0. And then just moving this to the other side of the equation, we see that the integral of C1 and C3 are the same. So the integral of C1 and C3 are the same. So notice that they're both going around the origin. Okay, they're both are going counterclockwise, and so this is 2 pi. So this one must be 2 pi as well. This is true about any loop that winds around the origin. Okay, so I imagine wrapping a string around and then tying it to itself, and if it wraps around the pole that I stick in at the origin, then that is going to be 2 pi. If it goes the other way, it's going to be negative 2 pi. And if it doesn't wrap around the origin, if it just wanders around here, then it's 0. All right, so that's a fun little thing to think through. That you get these different things depending on whether I go this way or the other way. In fact, if I go more than once, then it's going to be 4 pi. Like if I do it twice, it's going to be 4 pi. If I go the other way twice, then it's going to be negative 4 pi. This is something that's called the winding number, and it's kind of a cool way to think about wrapping some string around. Imagine there's a vertical pole sticking out of the page here, and then just kind of wrapping it around here, seeing how many times you go around it. Okay, one thing that's kind of there's a little bit off to the side here, but let's say we try to actually find G. So remember, I said this is not a conservative vector field, right? So it's not possible to see that this is equal to gradient of G. Nevertheless, we can try to do it and see what happens and see where the process goes wrong. So G sub x is this, G sub y is this. Okay, I'm going to use y here. I mean, you could do it either way, but it's a little easier to do it this way. This is the integral of this with respect to y. Do this substitution. U is equal to y over x, and then just plug it in. You get integral of 1 over 1 plus u squared du. I'm skipping a step here, but it's not, you can fill in the details. This is arctangent of u. U is y over x. This is arctangent of y over x plus an arbitrary function of x. Okay, take the partial derivative with respect to x, match it to this, you'll see h prime is 0. Anyway, g is going to be arctangent of y over x plus c. And if you realize for a moment, arctangent of y over x is actually the formula in polar coordinates for theta, right? G of xy is equal to theta plus c. So in other words, let's take like say c is equal to 0 here. Then here it's going to be 0. Here it's going to be pi over 4, pi halves, pi, 3 pi halves, and I go all the way around, and it's going to be 2 pi. But that doesn't match the constant that I had here before. Okay, and here you notice that no matter where I'm, like here it's at 0, here it's 0, here it's 0, here it's pi halves, pi halves, pi halves. It's just like this helicoid. Basically, the graph is a helicoid. This is not going to give you a function because when I wrap around, I end up with a different value. Okay, and of course at the origin is where everything goes crazy because the origin, this doesn't make sense, and theta is meaningless at the origin. Okay, just a piece of terminology here. A region is called simply connected. There's a region in the plane. It's called simply connected if every loop contains only points in the region. So here we go. This is simply connected here because every loop in the region only contains points in the region. Here, it's not simply connected. If I take some kind of loop that goes around here, then it contains this point that's not in the region. So if it's missing points basically in the middle, missing a point on the outside is not a problem. Missing a point in the middle is makes it not simply connected. So this is simply connected. This is not simply connected. And here we go. If a region is simply connected and q sub x equals p sub y is continuous on this region, then pq is conservative. In other words, all of these would be then equivalent if it's a simply connected region. Okay. Next time, we're going to talk about div, grad, and curl and all that. Div is divergence, it looks like this. Grad is gradient. We actually talked about gradient already, so you already know what this one is. And curl. So that's what we're going to discuss next time, and see you then.